Hello and welcome to Partial Differential Equations, the new video series where I want to talk about the theory of partial differential equations. And I can already tell you, this topic is often abbreviated to just PDE. We will also do this here, and moreover, since this is a really huge subject, you can expect a lot of videos in this series. However, before I start telling you what we will cover here, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget that you can download a lot of additional material with the link in the description. And now without further ado, let's immediately jump into the description of this video course. We will do a classical approach by first discussing the three most important examples of partial differential equations. All of these will include the famous Laplace operator, also often called Laplacian and denoted by a capital delta. And the first PDE here is just Laplace's equation, where we just search for solutions for the Laplacian. This will be already interesting, and of course I will explain more about the partial derivatives that go into this equation. And then the second PDE is the so-called heat equation, where we also have the Laplacian, but also a first order partial derivative with respect to a time variable t. So you already see, this is a different kind of PDE, and it has a lot of applications as the name suggests. And in that sense, the third type also has it in its name. It's the so-called wave equation. And this one also has a right-hand side given by a partial derivative, but now of second order. So the three equations look similar, but these details here completely change their behavior. And because of that, one has some special names in the theory of PDEs. The wave equation is a hyperbolic one, whereas the heat equation is a parabolic one. And finally, Laplace's equation is a so-called elliptic one. So the overall idea here is, if you understand these explicit examples of PDEs, you can lift these to the general cases. And indeed, this is something we will do afterwards, after our discussion of these three types. This will be a more general, abstract theory where we talk about Sobolev spaces, distributions, and so on. But this is definitely something I will do later, and maybe I put some stuff into a separate series like I've already done it for the distributions. Speaking of that, I should definitely tell you the requirements, the other parts of mathematics you need to understand this video series here. So let's put the PDE course here in the middle, and then I tell you which other series you should watch before that. In fact, the most important requirement is the multivariable calculus course, because there we define partial derivatives. And obviously a PDE has partial derivatives as the main ingredient. If not, we only would have an ODE, an ordinary differential equation. And of course it makes sense to first learn about this case before you go to the partial differential equations. In addition to that, I also would say it's important that you know how to integrate in higher dimensions. And for that it's sufficient that you know my multidimensional integration course. You might know that I also have a measure theory course for the general theory of integration, but it's not really necessary for our PDE course. Still, there are some connections between the two series that might help you, but it's not really necessary. The same I would say for the functional analysis course. It's good to know some operator theory, but it's not really needed. Indeed, this is something that we might need in the end when we go to the abstract theory and talk about Sobolev spaces. So you see, my idea here is to assume not too much, such that I can explain everything at the spot inside the series when we need it. Okay, so with that out of the way, we can immediately go to the first definition to answer the question, what is a PDE? This definition is quite easy to explain, because we already know that partial derivatives should play a role. And these partial derivatives come from an unknown function we call u. And the domain of u we call omega, and it's usually an open set in Rn. Otherwise, the values of u should be real numbers. So now please remember, omega is definitely a subset in Rn and usually open. In fact, in a lot of cases we want to have even more. For example, it's usually also connected. However, this is something we will talk about later. Here just remember that we have an open set and the dimension is greater or equal than 2. Obviously here, if n was equal to 1, we would be in our ordinary differential equations case again. Let's finish this definition. So we have an equation where partial derivatives of u are involved. So more formally, we could write that we have a function capital F, and then the first input is a point x from omega, then the second input is our function u, and then all the other inputs are given by partial derivatives. And there you know, these can always be written with a multi-index alpha, so we have d alpha u for a partial derivative. And then obviously all possible multi-indices could go in, but there's definitely a highest order, and we call this one m. So for explicit examples, we can choose a minimal m here, and this will be the order of our PDE. And of course, we can always write this equation such that we have a 0 on the right hand side. So this formulation already explains what a PDE is, but to make it more precise, we should evaluate all these functions at the point x. This means we have u of x here and all the partial derivatives of x as well. With that, our capital F is now a well-defined map, which gets omega as an input here, r as an input there, and a lot of Cartesian products of r there. Of course, this is just a formal description, and what we actually mean you immediately see in an example. So for example, we could say we have the sine function where u of x goes in, and then maybe we add the first partial derivative of u with respect to x1, and then maybe we multiply this with the second order partial derivative of u, and this one should be with respect to x1 and x2. And as before, everything here is evaluated at the point x. And there you see, the highest order for the partial derivatives, this m that is involved here, could be chosen as 2. So this is the minimal choice for our m, and therefore we say that this PDE has order 2. So it just means that the highest order of partial derivatives that is involved is of order 2. So maybe let's look at a very general example where d alpha u is involved. And now we could say we sum them up to order m. And what we get then is a PDE of order m, and we would also say it's a linear PDE. It is called linear because all the partial derivatives go into the equation in a linear sense. And please note, also the function u goes in linearly because it corresponds to the multi-index just given by zeros. Which also tells me that in the general description here, we should actually exclude this case in the third part. Okay, but now the term linear also allows for coefficients in front. So if we want, we could just take functions a with index alpha. So multiplying with functions that depend on x but not on u is allowed. Moreover, this is actually what we would call a homogeneous linear PDE, so we can also make it inhomogeneous. Which means we could have a function f on the right as well. Obviously, for the general description, we could just subtract this to still have a 0 on the right hand side. But for a linear PDE, this is a common choice to write it. And in fact, you can see this as a definition. This is exactly what we call a linear PDE. And now for the last definition of this video, I want to tell you what a solution of a PDE is. In fact, what we have here at the start is a so-called classical solution. So you might already see here that later in this course we will also define other solution notions. Why these other notions will be helpful we will see later, but first let's stay with the classical term. And indeed this term is not complicated at all because it's just given by a function u defined on the whole set omega. And moreover, we need that all the partial derivatives of u that are involved in the PDE are well defined. So the best case would be that we have partial differentiability for all the orders we need. So in any case, if everything here is well defined, we can put this stuff into our PDE. And then we just have the pointwise equality for every x in omega. So you see, this totally makes sense. For every point x we want to put in, the equation should be satisfied. And this makes it a classical solution, as you might already know it from the ordinary differential equations. And for now, we will keep this solution term, but please keep in mind that other solution notions also exist. But this is definitely something for the future, because first I want to talk about Laplace's equation. And let's do that in the next video, so I really hope I meet you there again, and have a nice day. Bye bye.